today I want us to go into a different area, which is where the class of today starts from. We want to look at the types of these deep neural networks. We want to try to unravel to understand what are those deep neural networks available out there, and how do we differentiate between different tasks at which we could use them for. The first one we addressed earlier on, if you remember, we talk about the one that deals with images. So anytime we have to start object recognition images, we talk about the convolutional neural networks or the CONVNet. They are primarily used in vision and image classification problems. So anytime we talk about image recognition, object detection, and so on and so forth, this is where the convolutional neural network comes. And that's why last time I was telling them in the classes that we need to, in developed countries, we use them in different sectors, ranging from astronomy, where we are able to study the galaxies, the stars, and all those formations in the universe. We also use them in climate change to be able to study, for example, satellite images that have been picked up in the 60s, 70s, 80s, and the contemporary time to be able to see maybe a change in the topography or the river basin of body and all that. We could be able to see how the world is getting better or drier, or we observe so many complexity. Even in medical health, we use these images to study the internal organs of humans. Now, we could in some manner deploy it in areas of security. For example, analyze images that have been collected by security agents in crime scene, and so on and so forth. So it's very, very useful sort of method where you could use in so many areas, especially in developing countries where they are having issues around insecurity. Like I said in my previous classes, that Nigeria, for example, could harness this kind of technology in order for them to augment the current security architecture that they are struggling with. Now, there is also the recurrent neural networks. The recurrent neural networks naturally do well with natural language issues or processes. Now, when we talk about natural language, these are the human sort of language that has to come in form of speech, or in form of sense, or in form of text. So this sort of architecture of the deep neural network do very well when you are having this kind of multimodal data that has to be centered around text, or speech or sign, or even sequential data like time series. Now, we also have another very interesting one called the autoencoder and variational autoencoders. So these ones are very, very interesting data set that has to do with unsupervised. They do with encoding unlabeled data into a compressed representation and then decoding the data back into its original form. So this makes sense because again, there are times we have lots of these text and images that we don't have a label for them, and it's completely impossible for us to find human beings to do these things for us. So when we, just like in traditional machine learning, when we have things like PCA, TSNE, UMaps, and all that helping us to understand this data set from the perspective of exploring the data-driven approaches, the same way we could use the autoencoders to help us to be able to understand this unlabeled data. Then at the end of the day, it could return them back to the original format, and it has already observed a pattern. And because of that, we could be able to say, okay, this is the kind of signals we are picking. So this data set should be called this. This one should be called this, and so on and so forth. So in the class of these kind of autoencoders, we have the generative adversarial networks, or GANs. We also have the diffusion models and the transformer models. Now, the transformer models, these are where the things like ChatGPT, BERT, and all those interesting transformer architectures spring up from. Now, you could now begin to see why you enter the text and tell ChatGPT do this, and then it quickly assemble those things and give you results. Although we cannot argue the fact that it's been trained with so many data that could be labeled, and some of them are unlabeled. But again, we see that it has the capacity to be able to manage or use or utilize this kind of data to make meaning from them. Now, if we zoomed into the convolutional neural networks or the COVNets or the CNNs, we will see that the main purpose of this kind of architecture of the deep neural network is for us to be able to process data sets that comes in form of images, in form of videos, to recognize patterns that could make sense. So we are interested in either we want to detect an object or we want to recognize a particular pattern. So it could come in form of the facial recognition problem. It could also come from object detection, like I emphasized earlier on that in crime scenes, for example, and maybe there are CCTV cameras. The robber could cover their faces or something, so you won't be able to see their faces. But there is a way where you could be able to get thousands of the images or whatsoever you have, and you begin to match them. Now, once you begin to match them, you will get to that point where the network will begin to look at things such as the height of that particular robber. It could look at some certain patterns that you don't easily spot them. And by the time it match them, even though that robber may have wear marks, it will be able to identify close match. Then when you get those close match, you pick those close match and further be able to start your investigation on them. I read of a story one time of these robbers that went to a bank and stole a lot of money from the bank. So what the analysts they did was to first of all analyze all the bank notes, and then they now they noticed that okay, this money that they took were mostly money that were printed within a period of time. So they focused now on all the notes within that period. Then the next time they now started zooming on the different people that this money is likely to go to their hands. So that was how they started following that. They replicated it in some of a control environment. Then they now decided to extend it to the general population in that locality. So they continue to trace it until they trace that money from the hand. So they started, like, if a particular transaction is done with this customer, they match that particular banknote to see if it agree with what they already have in their database. So they continue to track it until when they track it maybe to a store, then they ask the person who gives them the banknote. The person was, oh, somebody came, do you have the detail of this customer? Then the person could tell them, oh, this is the receipt. They would look at that receipt. So they continue to track until they caught one of the robbers that was responsible for it. So when they caught that one, he now led them to the subsequent ones. So there is this way you could be able to recognize objects and demystify mysteries using this kind of networks. So when you look at the architecture of the convolutional neural network, you will see in this case, we looked at the input, which is an image, which can be a handwriting, for example. You have the first layer, which is called the convolutional layer, and then there is the maxful layer. So what this does is that it's sort of reducing, downsizing. You can see the first layer was 5 by 5. The second, or the max layer or max pooling layer, was 2 by 2. The next curve 2 layer was 5 by 5. The next one was 2 by 2. Then it gets to a layer that it decode or flattened what it has already picked. So what it does, it will zoom into each of these objects and begin to look for, pixels, and begin to look for patterns. So these pixels, you can see them in form of a matrix. So if we are talking about 5 by 5, it means that on each of these 5 by 5, you still divide them into 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. So it will look at, let's say, 1, 1 versus 1, 1, 1, 1, 1, 2 versus 1, 1, like that. So like just like the way you have a matrix that it's let's say 2 by 2 matrix. Now you have 1, 1, you have 2, 1, 2, or 2, 2, like that. So it looks at that off diagonals and see which pattern can it find. When it finds that pattern, it will be able to to record that and moves to the other layer. So it continues to process until it comes to the final layer, and then it gives you the output. So for example, if we are feeding it with an image of a cat and a dog, it will do the same thing. It will identify what makes the cat so unique from being a cat, and then what makes the dog so unique from being the dog. And if you are feeding it with more than that, so we have that fully connected layer. So the fully connected layer is working with what these layers have already recognized. Then it will now carry out those linear combination that we are talking about. So in that fully connected layers, all what we are now doing is adding and subtracting the weights and biases. So this is also where the dropouts will happen, because at this point now we will look at which weight is important. The ones that are not important, we shut it down. The ones that are important, we could keep them. So stuff like that, all happens in that fully connected layer. But remember, before we get to the fully connected layer, we have to have the flattened layer here, which will open up everything that has been observed from the different layers, from the max pooling layer to the convolutional layer to the max pooling layer, and so on and so forth. So again, we said the structure is made up of convolution layer, like you saw, the pooling layer, and the fully connected layer. So each of these layers will be able to detect a particular segment or a particular pixels from that image that you gives it. So the early layer captures things like ages, colors, and deeper layers further identify things like complex shapes. So each of them will be capturing a particular thing as you're moving to be capturing, until when it comes to these fully connected layers where you begin to do the linear combination, and then finally you move to the output layer. So the advantage of this ConvNet is that it automates the feature extraction, which, like I told you, you don't need to do much about that. All what you just need to do is to make sure the images you are giving it, maybe they are of the same size or something, and quality, so stuff like that. So once you give them the image, they will do the feature extractions for you, and then it excel at handling high dimensional data. Of course, you know that when you are talking about an image, it's thousands and thousands and thousands of pixels. I know what that means. So it's quite a very heavy data. Then scalable and efficient for image classification. So once you are talking about image recognition, image detection, and all that, it does very well handling that. Now, the limitation again is that it is computationally expensive. Now, again, you can imagine if you are to look at satellite images that has to spring up from maybe 1980s, and then you want to compare all across this. You can imagine how long it takes from 1980, and the satellite images, it orbits the Earth, I think, every 24, 48 hours. Now you could imagine collecting that image for over 30 years, 40 years or something. By the time you have that kind of data that is quite large, that will be quite computationally demanding. Now, it required experts in fine-tuning and testing the model. So now, again, you have to tweak the parameters. You have to play with the weights. You have to regularize, dropouts and all that. So all this required expertise in order for you to have the optimal or the minimal parameters that could be able to give you an optimal result. Then again, may lose some data in pooling layers, but gain efficiency and reduces overfitting. Now, again, once you are doing all this transformation, there is that chances that you will lose a lot of data. For example, not everything that it will be able to pick. There are some things it will omit them because, of course, it's processing a lot of information, and that could be a problem. Now, remember we mentioned briefly about the recurrent neural networks, or the RNNs. Now, the recurrent neural networks, we said it's very, very ideal when we're talking about natural language data set or speech, which consist of things like speech recognition, text, sequential text, and all that. So it is very ideal when you're talking about sequential time series tags, also speech recognition sort of tasks. It works very fine with them. So generally, when you are having natural language processing issue or forecasting, then the recurrent neural network is what comes to your mind. So now you can see how we are building our understanding of this deep neural network. Convolutional neural networks takes care of images. Recurrent neural networks take care of text, natural language processing, speech recognition, and all that. So remember the differences between them. Now, how it works, it uses the feedback loop and memory of previous input in order to give us the output. So the output depends on the earlier sequence element that you feed this particular model. So what this whole thing is telling us is that it has this memory. Now, if you look at the earlier architecture that I showed you, you will see that we have the memory cell. So what happens in that memory cell is that once you feed it with, let's say, text, sequential text or something, it will take those texts and break them into tiny fragments called tokens. Now, these tokens that it creates, it will create a sort of a bag of words for them. Now, it will now begin to look at each of them and give them weight. Then it's from that weight that it will be able to identify what is important. So if you already train the model with this is a rainy day, and then your output is it going to rain today? The model will automatically knew that this is a rainy day. It's going to prioritize certain tokens in that sentence, probably to assign a weight of maybe 80 or 70 to rain and day and all that. So at the end of the day, when you're asking it for an output, it will be able to give you an output based on that input that you have previously used to train it. That's why at the first time that ChatGPT came out, you see that one of the problems it was having was hallucination. It was suffering from hallucination, meaning that it do not have the sufficient information to be able to give you based on what it has been trained. But because there is what we call in mathematics, when you interpolate sort of extrapolation. So what it does is sort of like an extrapolation. Then it will make up this information and then give you. So that's why then I think they have handled these problems in the recent models. But again, it's something that worth talking about. You discover that some of the things the ChatGPT gives you, they are not true, but it's very confident giving you this information. Now, when a good example then was references. When you ask it for references, it gives you references that do not exist. And there was this case of I think a particular lawyer or a judge or something in US that got into trouble because the case that he built and everything were interesting. He made some lot of references that were not true. So when they discovered that the case didn't even exist in the first place, but the ChatGPT gave him and he works with it and actually won that case, but only for them to discover that some of the things he cited never even exist in the first place. And in the law courts, most times it's built upon the previous cases that have already been determined by the jury. So when they now discover these things do not exist, it got into a whole issue and all that. So we said it uses the feedback loop and memory of previous input to get the output, which depend on those earlier sequence. So what happened is this is that if you have, for example, this word here, I am pleased dash 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 is so bad or something. It has this word embedding phase, like I said, which breaks this whole thing into token. Now, when it breaks them into token, it feeds them into the neural network phase. Now, there are hidden states, remember that we have. So those hidden states will process it, and there we also have the memory cells, which are likely going to be here. Then it will give a certain part of that sentence sort of like an attention. Then it will look at which of them is quite important and assign more heavier weight for them. And that attention is where we put in those weight. Then we have the component representation and the global representation phase. So in those phase, we have sort of max pooling and also the hidden layer, sort of deconstruction and also transformation of those texts that are much more important. And then finally, we have the softmax phase, which actually give us the output layer if we are okay with it or not. So the recurrent neural network, again, is very, very important because as we continue to proceed, we begin to look at things like transformer. You will see that these particular approaches are what is today helping us to write codes, do other things, so many things because of the kind of information that it was used to train them with. Now, the training of this recurrent neural network happen in sort of, because if it has a memory cell, then it do make sense if we talk about back propagation through time. So it uses what we call back propagation through time, or BPTT, to update the weight. And then it supports one to many, many to one, and many to many input output structure. I think last week I showed them how if I give ChatGPT a particular sentence, I tell it to write a poem for me of an Idoma boy from Benue State. And then I give it again the same sentence and say, write this for me. Each of the output it gives me will not be the same. So the same question, but different output, because the network is built to support one to many, many to one, and many to many output input structure. So that's why when you're using these AI tools like ChatGPT, Google Journey, and all that, you have to keep those things in mind, that the same sentence you give to that particular network it will give you the answers in different formats. Sometimes, yeah, the context may not really be different, but you discover it's not the exact things it gives you. And that's one of the things that makes this model quite interesting, because even when we as humans, we don't process information in the same way. So when you come to a class and tell your students or your pupils that this is a dog or this is a cat, there is that high chances in the next second you tell them what is this, they would answer you in chorus. One student may tell you, "Uncle, you said this is a dog." Another one would say, "I remember you said this is a dog." Another person would say, "Is this not a dog that you just said?" Now, can you see different context? So the same way this model processes this information and gives it to us in different format. So, but another thing that is important in all the three sentences that I made, this is a dog, uncle, you said this is a dog, or oh, is this not a dog? You can see that the dog keep popping up. So the dog seems to be the main character in that particular sentence. So definitely that dog will have some sort of a weight that precedes the other this is or something in the sentence. So that's one of the things that this model does. It looks at which of these. So each time you type and ask it a question, it will process it and then looks at what is important inside that sentence or question you just asked, and then it returns it to you. If you are asking it, for example, who is the US president? Now, it's very, very important. It will look at president, United States. Those ones take more weight than who is or something, in the sentence. Now, there is a variant. So when we say variant, it's like an offshoot of something, or in the biology sense, we call it mutations or something, or evolution of something. So the same way in the neural networks we have, in the recurrent neural networks or RNNs, there is an offshoot we call long short-term memory or LSTM. Like the name implies, long short-term memory. It means that the model has the ability to solve long-term dependency issue better than the basic RNN. So it means it has that capacity to be able to handle long-term frequency data sets and also short-term frequency data set better than when you just have a normal RNN model. So the advantage is that it handles sequential dependency better. It's also useful for temporal context and memory-based prediction. This LSTM, actually, I'm using it currently on acute myocardial infarction dataset that I have. So one of the things that I'm trying to explore from that particular using that model was that it discovered that most people, because I'm looking at comorbidity accumulation of patients with acute myocardial infarction. I think I could talk about this. It's not a problem talking about it. Now, the data set that I have is from the UK Biobank, and it's the ages of each of those patients when they were diagnosed with different diseases after they were diagnosed with acute myocardial infarction. So um, I wanted to look at the trajectory of their accumulation. Now, the trajectory of the accumulation is, of course, is not going to be the same, meaning that somebody could accumulate multimorbidities faster compared to another person. Now, when we talk of multimorbidity, it's the presence of two or more diagnoses or chronic conditions at the same time with a particular primary diagnosis. So somebody with, for example, diabetes could have several other issues like cardiovascular diseases, kidney problems, or something associated with it. But probably the person was first diagnosed with diabetes, but later on, these other subsequent diseases spring up. And we're beginning to see a lot of this issue in the developed countries lately. So it's quite a makes sense if we could understand how the trajectory of those people accumulate. Probably it could be issue that that is coming from poor diet or some sort of other factors that are contributing, and you could be able to advise that patient accordingly based on their trajectory. So I discovered that such kind of problem, if I need to understand it, then I need a complex model like the recurrent neural network. But again, because the trajectory of the accumulation of these patients differs, it means that the RNN cannot perfectly capture the problem for me. So I have to turn to the LSTM, the long short-term memory, to be able to explore the problem, which is what I'm using. So I'm using the LSTM to explore this problem for me, to look at each of these patient sequences and be able to give me the trajectory. So if I'm looking at their trajectory in 5, 10, 20 years, I could be able to use the LSTM to find them for me and put them in a group. So what I'm doing was quite an interesting thing. I'm using unsupervised learning that consider temporal analysis as part of it, not the normal k-means, to put them in group. Then when I have gotten them in groups, I now feed this group to the LSTM to find the correct trajectory for each of these patients for me. So quite a very interesting thing. So it handles this kind of time series sequential data set very well compared to the basic RNN. And again, because it incorporates the temporal context in form of a window, so what I does, I give it like a window because each of these patients have their window. So I could tell it in 5 years time, 10 years time, and over. So, but again, one of the problem of this recurrent neural network is that is prone to vanishing or exploding gradients. So remember we talk about this gradient vanishing and exploding, that when it's too small, when the value becomes too small, it gets trapped in these local minimals. And the moment you get trapped in this local minimal, it gets stuck. And remember, one of the things that could cause them could be wrong. Either you use the wrong activation function, the sigmoid, when maybe you're supposed to use a ReLU or a TAN or something. So again, you have to be very careful so you don't have vanishing gradients. And the vanishing gradient again can come because of sparsity. So you have to also look at the kind of data you are using so you don't have issues. Then exploding gradients again, when the value becomes so big. When it becomes so big again, it becomes just like when you put let's say water inside a kettle or something and you're boiling it. Even though you close the kettle, as the moment the water they get to that boiling point, it gets to a point it continues to boil, and before you know it will pop up the cover of the kettle. So that's kind of what we mean by exploding gradient. So when this thing continues to increase geometrically, the loss function, it becomes so big that at some point it's goes to infinity or something, and that could not be able to contain in your model. Now we talk about slow to train and difficult to scale to large data set. I told you about the chat GPTs that has billions of parameters, if not even trillions in some cases. You can imagine how long it takes to train this model and the energy it must have required to do that. And then we are training this model with all the data set that have been produced on the internet. So you can imagine how much data is being deposited in the internet. Even as we are talking right now, we're already leaving carbon print on the internet. Now, you can imagine all this data that have been produced, I think since from, if I'm not mistaken, the internet came in, I think in 1996 or 7 or so, when the internet fully took off. Now, imagine the data set the world has produced since that period, and these models have already been used to train all these data sets so far right now. So it's kind of crazy how large this data set could be, and you could imagine the challenges those guys could have faced trying to train the whole data on the internet, with this model. Complex to optimize with many layers and parameters. Like I said, the moment you have billions or even moving beyond the fourth layers, it becomes very difficult for you to be able to optimize them. Now, if you remember, we talk about the autoencoder and variational autoencoder models that we said those ones are responsible for unsupervised learning, approaches. So it do make sense. The Recurrent handle textual natural language processing. But now there are data that doesn't have label, and you want to get a label for them. So what do you do? Because clearly those kind of data, you discover that you cannot be able to handle them using the normal ConvNet or the RNNs. So you begin to think of an approach that you could be able to get a label for them. So in order for you to get a label for them, you need a sort of an approach that can help you to compress, reconstruct this data. So that variational or autoencoder, or we call them the VAEs, help us to construct and compress and reconstruct the data in sort of an autoencoding format, and then help us to generate some realistic variation of the data. So it makes sense if we are reconstructing that input. But for us to be able to do that, we need to sort of compress it. So if we don't compress that data, it's quite difficult for us to be able to reconstruct it. So we construct it in such a probabilistic encoder format. So if we have an input, let's say it's an image, we feed the data. In order for us to do that construction, of course, it's like a sort of like a if you know statistics, we talk about maximum sort of likelihood. Now, when we are talking about maximum likelihood, most times when we talk about maximum likelihood, we are just looking at how we approximate the mean around the standard deviation and error. So that's sort of what happens here. Then the moment you do that, and when you understand this, it means you are going to be doing sort of like a sampling. So if you have a population, let's say 1,000, you sample, let's say 10 out of that 1,000. So that's what we do. So that sort of sampling will happen, around here, and then we compress it. Now, when we're talking about this compression, then it makes sense if we bring in the concept of latent space, because this latent space talk about projection. So we now kind of project these samples that we are taking from the original data or population, we project it into another dimension. So that projection we are doing into the dimension that we are sampling from here is we is an uncompressed low-dimensional representation of the input data. So by the time we do that, we need to deconstruct that data, reconstruct it again. So in order for us to reconstruct it, then it makes sense if we are looking at the posterior distribution of the data, so that's sort of like a probabilistic decoder. So that probabilistic decoder is like a posterior. Now, if you understand maximum likelihood again, you will know that we have in maximum likelihood, we have the frequency and then we have the Proud distribution, which gives us the posterior distribution of something. Now, the same way it's happening here, when we project them, we now do the reconstruction using the probabilistic manner. So it's kind of, and of course, if you know probability, it's just that level of certainty that we have or confidence for that particular thing. So that will now reconstruct in the input space. So you see that another thing again is just like a mirror. So each time you stare at the mirror, the mirror gives you a reflection. So the same way you take the original image and you project it into a low dimensional space. When you project it into the low dimensional space, it reconstructs it for you. When you are looking at the mirror, you don't have any doubt that this is your object that is being reflected, or your image that is reflecting on the mirror. So it's kind of the same thing. When you're reconstructing it, you have that level of confidence that what you are reconstructing is actually correct. So the major architecture in the autoencoder and birational encoders is we have the encoder. The encoder does the compression of the data into dense abstract representation. Of course, it makes sense because you're kind of like, picking up and projecting it into the latent space. Then the decoder helps to reconstruct or generate a new data from the encoded space. So, but remember, the generation of the new data is not really going to be that different because you are having some probability. There are posterior sort of probabilistic nature that is coming from the fact that you already have some prior knowledge of that data before. So when you are reconstructing these new images or in the encoded space, we have that level of certainty. And that is why, again, it makes sense about things like ChatGPT. You see a lot of people using them. So a higher certainty, because these answers you are getting from the ChatGPT has already been used. They have already trained information about them. So if you are asking of a poem about an Irishman, the ChatGPT must have been trained with several poems that has to relate with Irish or something. And even if it does not, then it has been trained with poems that has to do with the century or that period or that time phase that those kind of people exist or this kind of information exists. So based on that, it's going to give you an answer with some level of posterior probability, about it. And that's why, again, if we have the chance to look at things like prompt engineering in the course of this class, you'll see I'll make emphasis on some of those things. That make sure you're giving the chatbot the prompts that are very clear and decisive, so that when it's returning the answers to you, it will return them with that level of certainty, and people wouldn't want to question it, because sometimes if again, the computer is more like garbage in, garbage out. So if you don't really give it a nice prompt, it gives you something that is not true. But there are people that are harnessing this large language models for so many things. They are using it to do their businesses, to be a research assistant for them, to help, and so many other things that these things are helping people out. But again, if you don't know how to utilize this critical information, you will not be able to get a maximum output from them. So the autoencoders or the VAEs handle things that like image and speech generation. That's why you see that you can give ChatGPT images, or you can ask it for images it produces you, and also speech generation. Like I talk about earlier on things like the Alexas and all that you could talk with. Also anomaly detection. Now, when we talk about anomaly detection, it's basically how to identify or deal with outliers. Always the black sheep you are interested in spotting. Then blurred or damaged image reconstruction. I saw recently this image on Facebook about an image, a blurred image that was fed on to AI and it reconstructed. And a lot of people were like, "Whoa, this image is nice." But again, I started trying to spot what was wrong with the image. And I think that's a data scientist or statistician. Sometimes you just find yourself observing things that you're not supposed to observe. But again, I was looking at the image and I saw that the original image, the people were not smiling, but the one that reconstructed by the AI, they were all smiling. And I was like, oh, this image is interesting, but again, they are smiling. So stuff like that. So it could help you to be able to reconstruct those damaged images. Imagine there are images that you would love to see them, maybe pictures from your childhood that are badly damaged and you don't know how you could be able to reconstruct it because you don't have the original negative of the picture. This AI could help you to do that. Although, like I said, it could not give you the exact thing, but again, it could give you with some level of clarity, which again, it makes a lot of sense. And again, these days you see a lot of AI videos and images online ridiculing a lot of people, president and all that. And sometimes if you don't even know, you would think these are real images. I saw one of that they did recently of airplane in a typical African rural sort of area, and people were entering into the plane with goats and different kind of things, and sort of fun, and all that. But again, AI is going to that particular point where we will not be able to fully deconstruct what is an original picture from what is AI generated. So we also got high dimensionality reduction and unsupervised learning. So again, you see that deconstruction projection from the low dimensional latent space, it makes sense if you give it an unsupervised data. It could handle it very well for you. It is like a foundation for generative AI. So the large language model you see, ChatGPT and the rest, stable diffusion models, they all spring up from this auto encoding format. So this is actually a picture of a cat that was given to the model. It does the encoding and also it reconstructs it by using the decoder and all that. And you can see, to that extent, you can see that clarity, in the reconstructed image. Now, one of the advantage of the autoencoders is the fact that we could learn, from unlabeled data. We could, find a lot of patterns. You could, make a lot of sense for us, and all that. It speed up processing, and it reduces our storage need. So in this case, we don't really need to have a lot of storage capacity to be able to use them, and the speed in processing is quite faster compared to the other approaches. It enables new data generation. Of course, most of the things we are getting from ChatGPT and all these large language model right now is completely kind of new knowledge. We are beginning to see new things that we have not seen before, we have not observed, even from all the data that we have mined so far in the world. So they are helping us to deconstruct a lot of complexity, a lot of things that we don't think it will be possible. Now we are beginning to see that these things are actually possible. So generating new text, new images for us that we never thought that these things we could see them even happening in our lifetime. It is very useful for classification tasks, anomaly detection, and so on. So these kind of models are very, very effective in classification and also, like I said, anomaly detection. So you could imagine if you are interested in spotting things like cancer, some certain kind of mutation, this kind of model could really help you to be able to look at the images and reconstruct them in such a way that you could see what is wrong. However, one of the limitations is that there is a high computational cost for this complex model. I gave you guys an example of the ChatGPT models that we always have, maybe ChatGPT 4, 3, and all that. It takes a lot of energy, a lot of money to be able to do this, to train this model. So the computational cost that comes with it, some of these things have billions of parameters, if not trillions. So by the time you looked at it, the energy it's also sapped from the environment. Like I said, the data centers get hot, processing the things where, each time you write a text in ChatGPT and ask it a question, we imagine the time it takes, the energy it takes to process it and return the results for you. It's quite enormous. And you are not the only person using these things. Probably there are millions of people, if not billions, all over the world that are using it at the same time. So it could take a lot of time and energy to be able to process this complex model for them to even just to train, you know. Now, it may fail to capture complex relationships. Um, Then there is the risk of simply copying input in unsupervised learning. Now, let's look at this famous image. Now, if you looked at this famous image, I think Lisa or something, you will see that when you feed the image, there was an issue when it was reconstructing the image. It gave it a manly look. If you could see, you'd actually see this was not the same face it gives. It distorted the face, and also even the environment. In the reconstruction, there are some changes in the environment. And all that. So this could be some of the issues you are having when you are trying to capture complex relationship, and also this copying and pasting that we're trying to do sort of, sometimes it doesn't go well. We don't get the actual thing that we needed to pick. Now, there is the generative adversarial networks or GANs. Now, the generative adversarial network also, work in similar manner like the autoencoders. However, it generates new realistic data, which could be in form of image or audio or video. It also might make training data such as human face, animal transformation, and so on and so forth. However, it generates this image from noise, and the noise here could be fake images or fake stuff. So it has a sort of like a generator where once you feed it the real image, the noise will create a distortion around it. So that distortion it will create, then it will now judge it. So if you feed it the real image, it will keep the real image, then it will look at the one you're feeding, generate some random images or noise around it or fake images, then it has the discriminator that will now judge if that image is real or it's fake. So you can see it has different from the adversarial, sorry, from the autoencoders. The autoencoders transformed, sort of from it takes the input, projects them in the lower dimensional space, and then it's give you all it gives you the decoded or deconstructed ones. But in this case, we have more like what is true and what is false. So if you have the real image you give it, it will now distort them. So after it distorts them using the generator, it will generate its own images from what it has learned from the real image. Then it has the discriminator, which keeps the real one and then judge if that is true or that is not. So quite an interesting thing. So the generative adversarial networks, the core components like you saw from the previous slide is the generator, which creates that synthetic fake data. Then it also have the discriminators, which evaluate if the data is real or fake. Then so these two components compete in a feedback loop to improve the quality. So you try to most times have a human in the loop to be able to look at these things and give it feedback so they continue to compete with each other. So what is true, what is false, what is true, what is false, in order for you to get a quality out. So the generator outputs data, the discriminators test it. So the generators will generate it and then feed it to the discriminator to detect if it's going to be true or false. So if fake is detected, the generator is penalized. Iterative training continue until fake are indistinguishable. So it will sort of that's why I said there will be some sort of someone to judge. So which the discriminator will be checking. So if the generator gives it one, it checks. No, it's not. It goes back again. Then if it goes back, it penalizes it. Now, when we mean what we mean by penalization in the modeling approach is simply trying to work with uh, reducing or tweaking of the weight or biases. So what we are just playing around is okay, we use 5. 5 was not giving us what we need. We reduce it to maybe 4.2, 4.3. So that's kind of back and forth tweak that we do until we get the optimal thing. It's very, very important. So, for example, we could have this kind of plenty images, and then we add, these images, and the first thing we do, like we tell it to add, remove smiling, add glasses, remove glasses, stuff like that, or even that of a horse, and then we tell it to color it, in form of zebras. Now, application of this is very important when we are doing image synthesis, e.g. the deep fake, and then the style transfer, like a horse transformed into a zebra, then data augmentation for ML models, because sometimes we don't have enough data set for us to use for training. So these adversarial GANs sort of can help us to generate these random data that we could virtually use them for our subsequent training. So one of the advantage is that it could get to that point that it will generate this realistic output such that the image it will be very difficult for you to decipher what is true and what is false. Also, we could be able to learn from unlabeled or minimally labeled data set because if we don't have a lot of information about it, if we feed it to the gangs, it will be able to give us a lot of information because it performs some sort of distortions. Um, it enhanced the training data diversity. Like I said, if we have limited training data, then it did make sense if we find a way to create artificial data that we could be able to use for the training. However, one of the challenges, yes, it's computational intensive, like all deep neural network models, and also the mode collapse, because sometimes it runs out of having this to generate these random images because there are limited varieties in the inputs that we have given it. So the generated output will also follow suit. And the training may take a long time to stabilize. Like I said, because it's something that has to do with back and forth, you check if it's true, if it's not, you penalize and all that. It could take you quite a long time to come to a consensus about how to be able to minimize what is true and what is not. So another thing again, it generates faces of people that don't even exist. Yeah, so some of these images you could see, they are people that actually they don't even exist in real life. But yes, of course, it will generate them because you asked it to. Now, another very important thing is the diffusion models. So the diffusion models are again it's an offshoot again. Remember, we are looking at offshoots of the autoencoders, right? Or the VAEs. So the diffusion model helps us to generate this realistic data, mainly images. It starts with a random noise, learn to denoise it into a meaningful output. So on the other hand, the diffusion model learn from the random noise that it has created and then try to remove them. So when you have when you generate a realistic image, let's say a dog, you feed it to the image encoder. So again, the latent space. So remember what we said from the previous autoencoders that the latent space will try to, what it does is projects them. So when it projects them, it adds this noise into them. So by the time it adds this noise into them, the next thing is it will try to denoise it by performing a reverse diffusion. So that reverse diffusion is like, you go this way, you're coming back in a reverse. So that reverse diffusion, you need an image decoder, then it finally outputs the generated image. Now, when you look at this image, you could see that this is the real image of a dog that it first feeded, but when it was returning back, you see that the dog it gives us actually the ears are kind of big, and the dog it gives us it seems to be actually standing. But altogether, we can see this is also a dog that it actually gave us. Now, so there is a feed-forward process where we add noise to the training data until we cannot be able to recognize it. And then there is the reverse process where we learn to remove the noise and reconstruct the data. So train by minimizing the difference between the real and generated image, or the generated and the real images. So the advantage of the diffusion model is high quality image generation, stable training, no adversarial setups like in the case of GANs, then fine-tune, fine control over the generation process. So you really have that control over it. It's less prone to mode collapse. So again, you don't run out of images to generate like the mode, like the case of the other one that we looked at. You could see that in the case of GANs, one of the problem it has is because we are trying to decipher between that fake and real. But in this case, we are adding noise, then we deconstruct it again. I could actually see quite an interesting images that was generated from the diffusion model. You can see very, very nice, smart looking images that it gives us, very high quality kind of image that you could get. However, one of the challenge again is computationally intensive, even more than the GANs. So it's quite intensive. Then you need care in fine-tuning the model. It's vulnerable to backdoor attacks. It can be manipulated to generate bias or altered output. So again, there are vulnerabilities which others could explore, and distort the original output that you intended. Use cases, text to image generation. One of it is the DEL. As the DEL-E, or the DEL-E, it's very popular for using, you put text and it generates image like it's kind of everywhere. I think I've used it some few times to generate images. There is stable diffusion model as well. It's kind of everywhere that you can play around to generate different kind of images. It's very good for creative media, art, and content generation. So when you want to generate this nice looking top-notch images, I think the stable diffusion or DEL are very, very nice for you to explore, Now, we also have the transformer models. Now, the transformer models, which become very popular, they power the large language model, which virtually became the chat GPT that is everywhere today. Their core architecture spring up from having an encoder-decoder structure for text processing. The encoder takes the raw text into embedding and then the decoder makes predictions by predicting the next word based on the context. So you have the inputs where you put in your text, you type in this is a man or something, this is a dog, this is a woman, this is a girl, anything you want, you ask the chat GPT chatbots, and then it will take that word, via the embedding phase or during the training. So when we put the input, it embed them. Now, like I told you that what happens mostly in the embedding phase is, we break them into tokens. Well, when you break them into token, you put them into this bag of words, and then from there you can begin to assign weights to them. So there is that encoding layer and the multi-head attention. So that multi-head attention is where you begin to prioritize and say, okay, if you said this is the president of US, it will prioritize things like maybe US and president, and then it gives them more weight than the other one. So it learned via the feed forward method, and then it gives you that output sequence. And then you also have the decoding layer. In the decoding layer, of course, the decoding is for predicting the next thing. So when you are typing, for example, if you have used those ChatGPT, you could see that those things gives you respond based on what you have already given it, and it can be able to make that prediction based on what you have already given it. So that decoding layer handle that kind of issue, where again it will focus on what is most important in that prompt that you give it, and then it gives you back via the feed forward method. So we said that the key innovation in the transformer modeling architecture is that unlike the RNNs, it processes text in parallel. So because it processed the text, you could see that it has this different layers. There is a layer that handles decoding. There's a layer that handles encoding, which is not when we are talking about RNNs. They seems to be all, packed up together. Then it learns the word position and relationship. That it is context aware. So because of the attention attributes that it has, it's be able to focus based on what is important. Because if you're talking to someone, you know that it's not every words are not the same. They carry different weight. When you are saying this is my father, you know that father in this case is very important. Mine is also important. So it focuses on what is important in that particular sentence, and explore that relationship positioning in that text. Now, we have it can be pre-trained without specific tasks and can be easily adaptable to many natural language processing tasks. Although on the issue of pre-training, we were talking about with one of my colleagues I think last 2 weeks when I was at the office, we we're talking about how it's not really make sense for us to use pre-trained models, from this large language model, because according to him, he felt that a lot of time when you are coming to use the pre-train, it's like these things were trained using a lot of data set. And when you are coming to adapt it, maybe your data is very, very tiny. So it's like a tiny fraction into what has been done. And going by the normal machine learning approach or knowledge, you know that each time you are having that kind of problem, you're already setting up your model for overfitting and underfitting sort of issue. So, his argument did make sense about, he suggested that instead of us using the pre-trained model, why not we shift our attention into using something like RAGs, so we could keep the data to sit there, and we could use the RAGs to communicate with this particular data and be able to observe, sort of agentic AI. And of course, I wouldn't want to bother you with that, but I'm trying to make you understand that you could use the model that has already been trained on not a specific task, and then you could adapt it and use it for your own problem. So the use cases of the transformer model is that you can see non-generative tasks, such non-generative tasks like text classification, entity recognition. You can use the transformers, not necessarily like the other ones like GANs and the rest that you have to, generate artificial or fake things. But these ones you can adapt them and use them for normal text classification or image recognition. Also, you can use them for generative tasks such as translation, summarization, question and answer, and even text generation. Like I said, sometimes you could tell it, write a poem for me on something, and it could, write, you can even write an essay, it could write, a whole book or something for you. So you could do a lot of generative tasks as well. Now, the advantages is that it handles long-term dependency in text. I think for Google or ChatGPT, I think it will take up to 500 token or 1 million token or something. So you could see that kind of memory that it has, to be able to handle this kind of long-term dependency in text makes it quite super strong or powerful. Uh, it's scalable, adaptable to various tasks. Like I said, you could pick up that pre-trained model and adapt it to a specific task that you want to do. So you could see the same ChatGPT large language model that was used to train problem in engineering. You could pick it and adapt it to train a problem in medicine or even in bioinformatics. Um, it enables large pre-trained models like ChatGPT, BERT, etc. So again, you could be able to, use them like we are seeing today in the case of the ChatGPT and BERT. You could adapt this heavy model that have been used to train a lot of things. You can use it, to your own issue that you're looking at. It requires less labeled data for fine tuning. So you don't need to have a lot of data to be able to do the fine tuning, which makes a lot of sense. It means that just with little understanding of how these models work, you can be able to adapt them for any other task that you are looking out for. So like I said, the architecture, we have the embedding, and we have that decoding encoding phase. So we have that embedding input, which of course here is where we have the activation function. Then remember we talked about the multi-head attention phase, and then we have a phase where we add and also normalize, and it works by feed forward, and then it moves also again to the next phase. Now, the same thing also when we are outputting, so it will look at the probability again about how these things moves out for. So the same thing, that encoding phase also could happen in the decoding phase. So the same different layers, you add them and transformation happen, but everything happen in a feed forward sort of, and then finally you could get the output. Now, one of the limitation of this transformer model is that it demand high computational cost and training time. Some of them takes up to 2-3 months, 6 months, depend on the resource that you are trying to use to train them. To actually take a lot of time. That's why a lot of people just adapt the pre-trained model for their specific tasks because of the time factor. Then it need large, clean, and unbiased data set. So again, you have to make sure the data set that you are using is quite no, it makes sense. Don't just feed it with any kind of rubbish. Again, I make that emphasis that AI is garbage in, garbage out. So make sure you're giving it a good data that it could be able to give you nice response. Now, the common application of this deep neural network in real life in things like application modernization. So most of the time, industries, organizations, and so on and so forth, they are beginning to migrate from the normal traditional way that they do things to begin to leverage these large language models on their organizations. For example, you could help them to train their database on public code-based issues, down to customer response, down to different departments. You could bring in this large language model to help them to be able to understand their duties and facilities better. You can also use it in text prompts and generate or translate even the code that have been written before. So we now see that this AI, like ChatGPT, give us the opportunity to train things that was done in SAS, SPSS, R, and other languages like C++ and all that. You could pick them now and tell them, I want, like, sometimes I play around with code. There are codes that are written in R or scripts, sorry. I could take those scripts and tell ChatGPT that, okay, can you quickly just turn these scripts for me to Python? And then I could use that script, for my subsequent Python chat. So, and sometimes, again, I could also use uh, Python scripts. I could turn them to R scripts and use them in R. So that translation could help organizations to create a clean, maintainable code, that they could be able to work on. Auto generation function could help them to generate different functions. You automate them. There are so many tasks right now that people are running one-man organization, where they have agent AI doing all the tasks for them, down to writing of email, read posting on social media platform like X, Facebook, and Instagram, and all that. So it could help to automate all this process. It translates things like language like COBOL and also things like Java. You could translate from that COBOL, which is a machine read language, to things like Java or even Python. So it helps you to speed up coding. Like I said, there are some code that could take me time to do, but now with the large language models, you could easily just feed them to the AI and you run them. It reduces manual work. So yeah, I think you don't have to stay to work over them again. It could easily just help you to bridge some of this skill gap. So we're beginning to see in the coming years, and even from now, if you go to places like China, they already have a lot of self-driving cars where you don't see human being in their Ubers. You just order an Uber, the car comes, you enter, and then it takes you to wherever you're going. You could just need to communicate with it. We see a lot of voice control assistants. We also see a lot of automatic image caption and generation, and then we see automatic machine translation. There is this AI data science podcast I normally put during the week. And most of the time, I just write the particular script that I want. Maybe if I'm writing on a particular subject matter, I think the latest one that I put, I saw some response from people on AI alignment. It talk about how and what is inside ChatGPT. And if you listen to that podcast, which you could go over it and listen, quite an interesting argument about the monster inside ChatGPT. It was on the paper that came up recently from Wall Street Journal. And they try to look, they train some model around and they try to look at the dark side of AI. And they discovered that the model was trying to discriminate between the Jews and Muslims and other people, compared to the blacks and other folks. So the emphasis I want to make here is that most times when I write this kind of script, I give it to AI, and then the AI do the voicing for me. Then at the end of the day, I do the other things like garnish it and the rest. And then when I listen to it and it makes sense, I upload it, and then it helps to educate people. Now, someone can use that kind of a thing. You can create your YouTube channel and all that. You can build in those things. You can leverage this technology. You can create your own brand. So this AI can help you to be able to bridge the skill gaps that exist out there. Now, there are also issues around computer vision where you can use those things like the convolutional, the CovNet that we highlighted earlier. You know, it helps us to be able to understand the computer to understand images and videos. In image classification, object detection, we use this CovNet to learn a lot of patterns from this large data set that ordinarily we cannot be able to do that. So organizations that are working in these areas, they could begin to harness this uh, algorithms or model to be able to make their businesses much more better. For example, they could automate those things, like in the case of lane detection in self-driving cars. In healthcare, we could be able to detect tumors from cancer images. Retails can use it for visual search and recommendations. Social media, face recognition and tagging and all that, it will help us to process thousands of images per minute. I still hope we will have time to be able to talk about some of the businesses that you could be able to start from all these AI and all that. So you can see it helps you with tagging and helps you to recognize some of those images. And I think we have already made mention of computer vision earlier on. Customer services. We see AI being used in different areas of customer services, such as acting as a voice assistant. It helps to analyze sentiments. When you look at the comments from your customers or from your subscribers, you could be able to analyze if they are satisfied, how can you serve them better, and how do you know what their complaints are all about. You can help to also recommend personalized shopping and support for your customers. Most of the time, there is what we call basket analysis, where it helps to guide our your your customers to be able to select the next thing. That's why when you are shopping online, if you pick bread, you are likely going to see a butter will pops up, or a sugar or something will pops up. So this kind of approaches is recommended by AI, and all that. So it helps to make the customer to understand your services or products better. It also helps to improve their satisfaction and also improve your yields or sales. And it gives you that competitive edge and advantage. So one of the common areas like digital workforce, we could be able to work everywhere now because this AI has made things easier. So remote working, we're going to be seeing a lot of people working from the comforts of their home, just like we're doing right now. And I'm teaching you, you are scattered all across the world, but I could be able to communicate with you because we have created a platform where we could all work together. So that personalization of learning via remote or virtual platform helps us to be able to create this blended learning environment. And the LLM can help us to extract tasks or information from conversations. It can be able to help us to create these no-code apps and all that we don't need to know what's happening in the front and back end. It can do it for us. I think if I'm not mistaken, the recent LLMs are beginning to give us platforms where we can even launch our app just from our idea. So you can imagine how these things are going or where they are going, faster apps creation and all that. So, like I said again, the LLM does a lot, but I think I'm going to stop here because I could